All right, hey folks, I got something old school to play for you.
Terms are believable. The first law of thermodynamics. Heat is work and work is heat.
Heat is work and work is heat.
Very good. The second law of thermodynamics. Heat cannot of itself pass from one body to a hotter body.
Heat cannot of itself pass from one body to a hotter body.
Heat won't pass from a cooler to a hotter.
Heat won't pass from a cooler to a hotter.
You can try it if you like, but you far better not.
You can try it if you like, but you far better not.
Just the cold in the cooler will get hotter as a ruler.
The cooler will get hotter as a ruler.
Just the harder body's heat will pass through the cooler.
Okay, so did you all get that? That was a review on the first law of thermodynamics. Heat is work and work is heat. Heat cannot pass from one hotter body to another. Whatever he said. We might have to do the closed captions. In any event, folks, we're getting into another round of thermodynamics. So in Chem 109, you all talked about the first law. And let's just put that down here. And just in case that little fun audio clip wasn't doing it for you. So first law of thermodynamics says change in energy, which we use as U. Change in internal energy of the system is heat plus work. Work is heat and heat is work, etc., etc., etc. Okay? We're going to be getting into the second law and third law of thermodynamics, all right? And there's an intimate connection with those laws and spontaneity or spontaneous processes. And by definition, by thermodynamic definition, a spontaneous process is one that occurs without outside intervention. So we're going to spend a lot of time thinking about what that means, this outside intervention. But here's a rather lovely example for spontaneity, I think at least. So we've got this beautiful looking Bel Air. I can't remember which year this is, 1965, something like that. Beautiful car, okay? And if we were to just let that car sit for a long period of time, we don't do anything to it. We don't touch it. We don't drive it. We don't do anything, as sad as that might be for this lovely machine. We know spontaneously, without any outside intervention, it will eventually look like this, right? Oops, it will rust. Maybe even if it was sitting in this like driveway and we didn't do anything to the driveway, all this grass would start growing around it. And we can say confidently, we know that it'll go this way spontaneously, but for us to restore this beautiful machine and get it back to where it was, that is not going to happen on its own without outside intervention, right? Somebody's going to have to come along and clean this thing, paint it, maybe fix the engine, all kinds of stuff. That's going to require outside intervention, okay? So non-spontaneous process, a process that only occurs as long as energy is continually added to the system. So keep this in mind when we're thinking about our spontaneity, okay? So another example of this, getting more into chemistry. So there's these cold packs. If you've never used these things, they're great if you have any ailments or aches or pains or whatever. So these things contain solid ammonium nitrate. So that's ammonium nitrate, NH4NO3 solid. And when you break these things, like you crack them to get them to work, there's a little water pouch in there that then starts mixing with the ammonium nitrate, and it makes it dissolve, okay? So now we've got dissolved ammonium ions and dissolved nitrate ions. And there's not any chemistry that's happening in this. However, the delta H, so the enthalpy to make this solution is a positive value, right? So that's endothermic. And it has to get that energy from somewhere, so it gets it from the surrounding room. And what it does as a result is it cools down its immediate surroundings and thus makes it feel cold, okay? And this happens spontaneously. So, of course, we have to mix the water with the ammonium nitrate, right? So, as soon as we do that, if we accept, okay, I do that one little thing, crack this thing open, but as soon as I do that, these cold packs become cold spontaneously, okay? And there's loads of other examples that we could come up with for what's spontaneous and what's non-spontaneous, and we're going to flush those out in more detail, all right? So we can also view spontaneity and other more simple systems that might kind of give us a clue as to what's going on in these spontaneous processes. So imagine we have a block of ice, okay? We don't have to study thermodynamics in great detail to understand that if we have this block of ice at room temperature, it is going to spontaneously melt into water. So let's write that down. Spontaneously melt at room temperature. We don't have to be like overly, technical to describe that, right? Or similarly, if I have some liquid water and it's at 100 degrees Celsius, we know it's going to spontaneously become a gas. So at 100 degrees, it's going to boil. Of course, we haven't put that energy, right? But you have to imagine, suppose we take one of these phases just into an environment that's at one of these temperatures. That's all we have to do. We take the ice cube, we put it on a table at room temperature, walk away. Undoubtedly, it will be melted, okay? But we know that won't happen the other way around. However, if we took some liquid water and put it in a freezer, we know that it would also spontaneously freeze at those conditions, okay? So this is a nice roadmap for how we can understand spontaneity, and we're going to start putting a little bit more physics and chemistry and math behind this stuff. Okay, I'll see you in the next video.